I want to thank everybody that is helping us make this successful and has come to hear Ben Connors talk about Scan Your Passions, blending X-ray CT scanning technology with personal interests. I'm Karen Brewer, coming to you live. And this is George Hodges coming to you also live. And of course, our guest speaker, Ben Connors. Ben, thank you so much for agreeing to do this for us today and to help share your knowledge and to help the community grow in their knowledge level and technology use and skills. So everybody understand, please, that we have all of the chats and all of the volumes turned off. Ben will be the only one allowed to speak during this time. At the end of the presentation, we will open it up for questions. Most of you will have your systems automatically unmute your mics. We have had some problems in the past with systems not allowing it through the firewalls or the bandwidth or whatever. So if you have a question at any time, put it in the chat box at the bottom, and George and I will be monitoring that. And at the end, either George or I will read the questions. If you choose to put it in an anonymous question, you can, but most of the time we will say who's asking the question and then let Ben have a chance to answer it. So without further ado, I hope that everybody, including me, has their phones muted. Let me mute mine before I'm the embarrassing one. All right, so without further ado, Ben, please take it away.
All right, thank you, Karen. Thank you, George. I'll just share my screen here in a moment. How you doing?
Perfect.
All right, awesome. Yeah, George, Karen, thank you. Certainly appreciate you guys putting this together. You know, and as I get started, you know, it's sometimes people do thank yous at the end, some at the beginning. I'll do mine at the beginning. But you know, appreciate you guys having me on. Also want to credit Justin, Mac, Jeremiah, some guys on our team here that really helped me put this presentation together. I mean, they're doing all the heavy lifting, and I'm just delivering it. Technology credits, so Nikon, Volume Graphics, the whole Avonix team. Just want to say thank you to everybody, because you know all of this is certainly a team effort. And I called George here maybe 40 minutes ago. We had a power outage, and so I was going to drive over to someone else's house so we could keep doing this. But power came back on. I'm back in the office, and away we go. So with that overview, so what we're going to be talking about today is, you know, I'll go, you know, brief company history, personal history, that sort of thing. X-ray and CT basics. I think most of the people logging in here know X-ray and CT, but sometimes with these virtual, you don't know who is logging in and starting to learn about X-ray. So I'll touch on that, but I'll kind of buzz over it. If I go too quick, you know, of course, you know, hit the chat and I can slow down. Enhanced technologies. So, you know, what are some of the nuanced differences, things that are new, or at least newer, and then really get into the meat of it. So, and I'll talk about it more as I go through the slides, but we have a project here, an activity called Scan Your Passions. So I'm going to talk to you about the physics of skiing, a failed model train, a record player cartridge, and the ring of death on an Xbox. So what we do is we scan things in our lives that we're passionate about. So we're mixing what we like to do outside of work with X-ray inside. So we can talk about pixels and photons, but in the context of maybe a ski boot or a record, rather than, you know, something benign and less interesting. So for myself, intro and background, I'll keep it brief, but you know, I've got a background in NDT. But first 7 years of my career, I spent as a technician. So it was, you know, UT, RT, mag, penetrant, CWI, all that kind of stuff. So I'm pretty familiar with the NDT business. The following 7 years, I joined North Star Imaging as a salesperson. Actually, I think when I was first approached and asked to be a salesperson, I kind of laughed and said, well, why would I do that? I have all these certifications. But what I learned is in that kind of an activity, you can learn about new technology, see a lot of new places. And then the following 7 years, roughly, I ran the inspection lab. So I you know, helped with expansion, you know, adding new offices, new machines, you know, different programs that we ran there. So about the last 4 years, I've been at Avonix Imaging. So I lead our inspection services business here, and working on expanding to different offices, different technologies, that sort of thing. So pretty much been in something X-ray or NDT my whole life. So scan your passion. So talk a little bit about personal side. First hobby. I don't know if wife and kids are really considered a hobby, but it certainly takes up a incredible amount of time and is certainly a huge blessing. One of the things we do as a family is we look to we're trying to check off all the state parks in the state, and ones close to your house are really easy to check off. And as they get to 3, 4, 5, 6 hours away, it's harder and harder. But it's certainly a family activity. Skiing, which I'll get to in a little bit, but liquid and solid. So in the summer, love to be on the water. In the winter, love to be on a hill or a mountain. Play a little sand volleyball, hunting and fishing, and youth sports coach. So that's kind of me in a nutshell. Avonix history. So I'll kind of go through a little bit of our company, organization, who we are. So Avonix Imaging was started by Brian Ruther and Jeff Deem in 2012. And I won't read every single one of these blocks along the way, but it started as a scanning business. Initial engagement was with Nikon, and eventually turned into a manufacturing business as well. So along the way, there's CE certification, ISO, opening a new office, adding team members, that sort of thing. In the near future, we'll be announcing new machines or new styles of machines, that sort of thing. We've got a new headquarters coming, as well as additional satellite offices. So that's kind of us in a nutshell. Core competencies as a company. I think I don't know how many participants we have on here. Most people know this, but we do X-ray or CT as an inspection service, which is my team, my role. And so we have AS&T and NAS 410 certified people, level 2 and level 3. We manufacture systems, we're ISO certified, and of course we repair and train and support what we build and create. What motivates us? So this is a big one, and it seems to come up over and over and over again. When we're looking to build a team, core values is really one of the key components. As NDT people, we often talk about certifications and qualifications and hours and all of this stuff. But a couple of years ago, as a team, we went through, what are our core values? What do we really want? So, we believe the goal, everything we do should result in mutual success for our company, employees, vendors, strategic partners, and most important, the customer. And we achieve that mutual success by challenging boundaries of human ingenuity, technology, X-ray products and services that we, provide or deliver. And then that leads to, the quality and safety of the things that our customers do, whether it's a rocket, whether it's a heart valve, whether it's a car, anyone in NDT, anyone in CT, you're looking at something really important, right? And so we strive for that mutual success because everyone in that whole environment has to succeed. And so we have it summarized in what we call ACE, so authentic, competent, and empathetic. On authenticity, show up joyful, humble, imperfect. We actually had some spirited debate on imperfect, and I'm really glad that it's in there. If anyone wants to raise their hand because they're not imperfect, let me know. I'll take your class. Grateful to serve others. That's really important to us. Competency, that's again very normal to talk about. We talk about it in George and I have had long discussions on certification of people and NAS 410. Can you make not just an image that you're asked to do, but can you make something beyond that? Can you see a defect no one else can see? So competency is really big. And then empathy, right? If we've got a customer with a lying down, a situation where they're really in a bad spot, we need someone on our team that is empathetic to that. both to their teammates, but also their customer or whoever's in that environment. So core values is really, really important. And it's a tool I wish that I had years ago. And I'm really thankful we have it now. And so we do a core values day. So we go and race some go-karts. We put some sandwiches together for homeless people or different activities of that nature. It's kind of an annual activity, but we should and do talk about this on a daily basis, right? We use it in our hiring, unfortunately, sometimes in the firing side of things, but you got to have those components to build a good team. So that's kind of my obligatory who we are as a company stuff. So next is X-ray and CT technology. So our lab, I've just got a picture of our Minnesota lab. We've got another one in Texas as well. And I'm just doing this for context. So once we get to the systems, you can ask about what tube, what detector, that sort of thing. So total within the Avonix environment, we've got 7 systems. We've got 2 LES or large envelopes. So these are either walk-in rooms or very, very large cabinets that I can stand in. They're typically, we're going to have a 450 microfocus X-ray tube, a 225 rotating target, 4343 is CLDAs, granite base, high precision, high-end X-ray. We've got a couple of Nikon XTHs, pretty legacy workhorse type systems. They're 225. Typically, we've got a rotating target as well as directional and sometimes a transmission, interchangeable heads on those. And then we've got like I said, a couple of systems that we can announce soon, but we've got a Avonix created 225 with a Nikon RT directional and a 4343 with a granite base and an XTV 160. So that's kind of the tools that we use within that X-ray environment. So what is X-ray and CT? And again, I'm burning through this pretty quick because I think we've got an educated crowd. So X-ray and CT is a non-destructive imaging method, which cross-sectional or volumetric data sets revealing kind of that internal geometry. I think we all know what the medical CAT scan looks like. So tube and detector spins around the body, and you've got one center axis of rotation. And in the industrial world, we like to joke that we don't care about our patients. And so in this case, the part rotates and tube and detector remain static for the most part. There's a couple technologies where that's not always the case, but for the most part spinning, tube and detector static. So and then the physical layout of that. So we've got basically an image of a system here. So on the left, we've got a detector. So very commonly that's either a 4343 or a 1621, some kind of a way to receive the photons. Lower down, we've got a CLDA or a curved linear diode array that's shaped to that cone of radiation so that we would have the same ray length, whether it's on the edge or in the middle. On the right-hand side, just a couple different example X-ray tubes. So RT 450 or rotating target 450, static 225, and a mini focus 450. So that's the general layout of a CT scanner. Once we would put a shell or some shielding on top of that. Some people use a concrete bunker. Others will have, some kind of a lead steel construction on the outside. So you got shielded doors that are interlocked. So if they, open the door, unplug the X-ray, radiation effects to specimens are pretty much always okay. There are some nuances. Typically it's space grade electronics or medical device electronics are the ones that there would be a concern. If we do run into that, you usually need to go backwards to whoever built that electronics or whoever's speccing that out, and they can articulate what kind of dosage that sample can take. But it's pretty rare most of the time. Whoever's bringing a product like that in is going to know that it's radiation sensitive and that there's a concern. And then, of course, a shielded cabinet keeps us all safe. So that's kind of the geography layout. So workflow. So, as parts process through an X-ray machine, scanning and X-ray acquisition, again, fairly straightforward. We just take 1,500, maybe 3,000 images as that part rotates. Pretty common effort is to figure out Nyquist, or figure out how many X-rays should I take based on what I want to see. Sometimes you can pull that back if you've got RQIs or different things like that that tell us I'm still seeing my defects, and then you can speed up a little bit. Surface determination. So in certain cases, we'll do a CT scan and then compare that to a CAD model. So inside and out, I can see whether that part fits both, from a defect perspective, but also from a metrology perspective. And that's, kind of a big reason for granite. So that was kind of the basics, or some of the basics. So what's the smallest defect you can see with CT, right? Anybody that's experienced on this call has had that posed to them, maybe in a lot of different ways. So resolution, X-ray and CT, it's complicated. Sometimes people say it depends. So the three main factors that determine resolution of an X-ray image or radiograph is detector spatial resolution. So smaller pixels, we get better resolution on paper, but smaller pixels are also less sensitive. It's a smaller photon bucket to receive that radiation, and smaller pixels are more noisy. Geometric magnification is another factor, right? And I'll get into each one of these. And then focal spot size. So the factor of the source energy and power, and the higher the power density, typically the larger the spot. So if you want a really, really small spot, you typically have to turn that down, and I'll talk in a little bit about how to deal and manage with that. But here's the basic math of geomag, source spot size, and spatial resolution. And a quick screenshot of a line pair. So, we would just image those line pairs and see where that both graphically and visually breaks down to detectability or lack of detectability. Imaging resolution. So like I said, pixel size, smaller pixels, they're not always better. They can be, but they can also cause some challenges. One of the things is that scintillator has to get thinner as our pixels get smaller, because if you have a really thick scintillator, there's a possibility of light landing on a pixel that we don't want. Maybe that isn't the best of process. It's got less active area, so that means we'd have to basically let it soak or light up longer, so more imaging time. And then more pixels, more problems. So anyone who's gone from 200 to a 100 micron panel, or even 200 to 150, you end up buying a lot of back-end IT stuff to store more, to manage more, to transfer more. So that can be a challenge. So geomag, again, I think we have mostly experienced people here, but kind of lays out fairly simple. So if we've got an X-ray tube on the left, a detector or an image on the right, and we've got a sample in the middle, relatively low mag, relatively close to the panel. And then as we mag up, we can certainly increase that resolution. This is, the purest or cleanest way to improve our resolution. It's just like if you're taking a picture of something, you grab that lens and twist it. That is the most pure way to get magnification or a better image. But in this case, as we magnify, then we're not getting my whole part. I'm only getting an AOI, or an area of interest of that part. So source to detector and source to object distance is really the calculation, are pretty straightforward here. The way I like to think about it is tube to detector here and here. Halfway between is 2x mag, and every time I cut it in half, I double my resolution. So 2, 4, 8, 16, on and on and on. And the image that we're showing, will flash that a little bit as we walk through here. So this is a sample that's not made for CT scanning at all. It's actually terrible. It's a little Inconel piece that's made for testing 3D printers. So they have, you know, pins that stick up, holes that go down, steps, these different features, and they want to see if the printer works well. So it translates well if you can CT scan something hard and see some void or defect or feature. That translates very, very well, especially in the aerospace additive world, where, you know, they don't make perfectly round things. You know, they make all kinds of different shapes, and we're able to see some of these defects, and it helps when you're trying to prove out. So not all mag is equal. So remember, in that calculation, focal spot size is one of the components, right? And so if we look on the left, a microfocus versus a mini, so a small, very, very small spot, 450 versus a, you know, relatively large, like a you know, 400 microns, pretty common. And each of them have their own place. It's not a good or bad. It's just a, you know, technical difference. But in the microfocus, and I'll show this in a few different examples, but in the DR, we can see all 5 of the pins and holes. In the mini, we can confidently see 3. And if you stand back far enough, you can debate the 4th. So same detector, same mag. The main difference is, you know, in school, what they referred to as the UG factor, geometric unsharpness. So that's just the physical focal spot size, the penumbra effect, as well as that magnification. So that's a consideration that all of us need to keep in mind as we're using geomag, because you might want to drive that tube a little bit harder wattage wise. But regardless of the tube or tube style, as we drive that wattage, that spot size has to grow, or we're going to have an electron beam welder. And we don't want that. So the easy concept to kind of communicate in layman's terms is a candle versus a window. So a point source versus a large light source, and the edges of that hand being fuzzy. And then resolution in CT. So we CT scan that NIST sample, and on the right, we're showing a 3 out of the 5, and on the left, we're showing 5 out of the 5 features that we wanted to see in there. So again, that was, you know, more of the simple end of X-ray and CT. Some of the advanced stuff. So I mentioned some problems and maybe how we can get around some of those problems. So one of the challenges in X-ray, and this is just pure X-ray physics, is you know, we've got a vacuum tube. We accelerate, you know, we boil electrons off of a filament. They accelerate in the vacuum. They impact that target, and about 99% and change of that energy turns into heat. So we all have to manage that or deal with that. And the last, I don't know, 0.3% actually of energy turns into an X-ray photon. So in a static target, there's finite heat dissipation. And this is, you know, the physics are true regardless of whose brand name you would be talking about. So if you want to crank up the kV, you'd have to have very, very, very low wattage, because, you know, voltage and amperage equals wattage. And so one thing that's done differently, and it's done pretty commonly in the medical world, probably not quite as much in the NDT world, is a rotating target. And so basically, if you're putting all of this energy into one very, very small spot, you know, one of the ways to manage that is have that target spin. So now we're spreading that heat or dissipating that heat throughout the rotation of the target. And so that gives a couple of advantages on the high end. You know, we can drive a 450 to a small spot size and see defects that, you know, maybe no one else is going to see. On the 225 side, you know, what used to be an hour scan can now be 15 minutes, which is pretty substantial. And so I alluded to this, but the typical reflection target, and, you know, we still use these today. You'll see in my examples, we absolutely use reflection today. it's about 1 watt per micron. So the basic math is, if you want to turn the kV up, you got to have very, very little flux, but we can squeeze that out. A rotating target is going to be about 4 watts per micron, so a 80 micron spot at 450. Another thing that's not talked about as much is the angle or the degree of reflection. So that 45-degree angle actually increases brightness a little bit. So we're dissipating the heat, we're playing with the angle, and we're able to light up a detector very well. And so that the kind of general spot sizes, if you are trying to get your head around what is possible, at 450, 80 microns, 100 watts, that's what's published. We've got some pretty confident evidence that we're down in the 50s there, but that's what we publish, so that that's what the case is for sure. At 450 watts, you'd be at about 113, and the 225, 10 at 30, and 160 at 450 watts. So that kind of gives you an idea of being able to do a scan differently. A couple of the other concepts, and again, this is, some of these might be our trade names, and I know others have other trade names, but what we call helical is basically, it's made for long, skinny parts. So you would put a part in, let's say a pen, or maybe a baseball bat or something like that, long, skinny parts. And when we talked about geometric mag a little while ago, if I would mag up on this pen, I would only get the ball point at a high mag. Let's say I'm trying to do a 10, 15 micron scan on it. Whereas with helical or some concept like that, whatever brand name you would look at, you're able to spin that part basically like a candy cane all the way up. And so we clean up some of these artifacts, clean up some of these defects, and you don't have to stitch anything together. So it's pretty slick. We use it pretty often. Offset CT. So this basically just increases your field of view. So the bottom right to me is probably the most useful view of this. So the bottom right hand view would be X-ray tube, sample, detector. And we can go out to about half of that cone and spin the part, because all that part goes all the way through. And I think George might even have some teaching slides on this, that you really only need about 180 degrees of rotation to get a good CT scan. Typically we do it for a lot of other artifacting and other reasons, but so anyways, that's kind of a slick one, the offset CT. And pixel push. So if you've got a spot size of a certain amount, and you're trying to squeeze out that last little bit of resolution for whatever the case may be, and again, this is I think Nikon came up with this first, but there's others in the market, and so the idea of pixel push is basically that the panel moves, panel moves, panel moves, panel moves. And I think I've got an illustration here. So it's 4 CT scans, so it's pretty data intense. But what we're doing is we're splitting those pixels in half. And so if I would identify a defect, see if I can get my mouse moving here, identify a dark or a light spot, whether it's a defect or anomaly in this area, and it shows up only in that bottom corner, you would then have enough overlapping for that to light up and basically show. You've still got some, issues with the detector. It's not a 1-for-1. Like if you've got a 200 micron panel, you're not automatically at 100 microns. But it does help to squeeze out a little bit more, and does help to improve. And then of course we check our panels. A lot of the aerospace work that we do, we're driven to test our panels, test our CT scans, test our people. When you're scanning things that fly, it's very, very important that we're confident on the quality of our product and what's happening there. So that's kind of the X-ray bit of it, the technical bit of it. Now we can get into the fun stuff. So like I'd mentioned, we have a project internally called Scan Your Passions. So this is a series or an activity where anybody in the company, right now it's mostly been the guys in the lab, but we have field service techs, we have manufacturing, we have engineering, we have other people in our environment that don't do CT every day, and we want them to be involved. And frankly, for me, I want our customers or other people to see CT differently, right? And kind of get excited about it the way I am. And so one idea that we had is that you can take your passion or your hobby or whatever it is in your life, bring it in and scan it, and then talk about that. Because if I CT scan a circuit card and show it to an electronics person, they don't care about it unless it's theirs, right? And that's true for all of us. We all kind of have a what's interesting for me kind of a hat on. And so what we did is scanned a few different things that we thought were cool and that some of our people are passionate about. So for me, it's skiing, right? I love to downhill ski. So I kind of started searching for pictures of skiing, and I wasn't sure if I could come up with something, but I did. So every weekend, every Saturday, I teach skiing. I teach little kids how to ski. I'm in a ski club. And, so we show up on these little Midwest hills and with a bunch of buses and teach the little kids how to make a turn on basically Minnesota ice. I have an app on my phone, tracks my runs and my speed and vertical and all kinds of stuff like that. I do this with, work friends and buddies. We try and take cool pictures, take my kids out west. Certainly looking for a powder day every single time we go out west. That's a super cool picture of just bumps covered in powder. You can kind of smash through them. Put, little mustaches on kids for a family fun day, and on and on and on. So I'm, kind of just trying to illustrate I'm absolutely passionate about skiing, and I certainly like X-ray. And this is a a little chance to mix the two. So out of that, we picked a ski boot to CT scan. So why did we choose a ski boot? It fits a scan your passion goal. Plastic, foam, aluminum, steel, all in one scan. So it's a tough scan, right? Low density and high density. That's a hard mix. And frankly, it allows me to Google skiing stuff during the day at work. So the physics of skiing. So if you back up a little bit, X-ray is just applied physics, right? Skiing has a lot more to it than one might think. So we've got a snowy surface, we've got a slippery ski, we've got the angle of that hill or that mountain, and typically what we want to do, we rate the angles of that. Green is for little kids skiing, double black is expert. So there's different hill ratings, but ultimately the physics of skiing is you want to make a turn as you're going down the hill. Some of it is to control your speed, but some of it is it's really fun, right? It's maybe analogous to a motorcycle on a curvy road. You kind of get that pendulum feel in your stomach. And so there's a lot of physics that go into that. From the steepness of the hill, the position of the skier, the engagement of the ski, which ski is engaged more, in a really high carve, perfectly pure carve situation. When you're carved like this, that ski is bent backwards, almost like think of it as like a leaf spring. And as soon as you flatten it out, it's going to pop you and you should hit the next one. So if you see a racer or a video of someone skiing, that's like the perfect situation where the energy of that ski and the energy of that gravity makes it really, really easy. Whereas a skidded turn is a whole lot more work. So the couple things that we think about in skiing is center of mass, right? So the three-dimensional balance point of an object. In a skier, it's going to be your pelvis or hips, something like that. And then base of support. So that refers to the area beneath an object, or a person. So every point of contact, supports that surface, and the boot's the most integral part of that. So if we apply this to reality, or to action, the image on the left, so that's a skier making a really hard cut in a slalom race. And if you look at the snow coming off of the two skis, the ski on the left actually has more snow coming off of it. He's probably got about 90% of his pressure on that outside, and the 10% is just a rudder or a guide on the inside. And so he's flexing that ski, it's going to pop, and he's going to bounce to the next one really, really quickly. The one in the middle looks like a middle-aged guy that's probably not as aggressively forward as he could be, but he's probably having a good time on vacation. And the one on the right is Teddy, our youngest.
Hands out front. Ooh, good one, Tiny. All right, do it again. Good job. What's that? Good job.
So the applied physics for those three people are the same. We're applying them differently. Teddy's got a little bit lower, base of support or center of mass, but the physics are the same. That boot fit actually matters for all three. And so, if we look at ski boots, what are they made of? What are we looking at there? They got to manage cold temperatures, large forces. A ski racer can get upwards of 80 miles an hour. A recreational skier, it's not uncommon that they get 40, 50, even 60 miles an hour. So they got to protect you. Every motion that you make, every engagement that you make, if there's slop in that boot, that's wasted energy and maybe even a wasted opportunity, depending on what you're trying to do or maybe even avoid. So this boot doesn't have a perfect shape. Nothing does. It's basically rolled up plastic, but if you unbuckle these boots, they'll kind of go like that over time. And so we use panel shift helical to be able to get that in a single pass rather than multiple scans that would need to be stitched together. What are we looking for in CT? In this scan, honestly, mainly for fun, but we're also looking at the liner to boot fit, the buckle construction. One thing that's perplexed me for forever is the walk versus ski latch. And I think this is true in skiing, but it's true in golf, it's true in fishing, a lot of other personal activities, is they've got these little widgets and you're like, man, that looks cool in the store. And then you get it home and you're like, does it really work? And then you just move on with your life. So we'll talk about the walk versus ski latch, general defects, voids, cracks, things like that. And then clues to a good fit. So the saying is the perfect boot should be just like Pink Floyd, comfortably numb. So that's really what we're looking for. So I've got a slice video here and it goes a little bit quick. So sometimes I just feel better if I slice like we're slicing through VG. So in this case, this is just kind of the bottom up or top down type of a view. So we can see some of these different fitments. If we look way up at the top, I'm actually able to see some voids and defects in that little walk ski latch. And we can see how the buckles go together, how the liner goes in, all of that sort of thing. Honestly, probably the most fascinating one, but we can't do it because it's not safe, would be buckle that on your foot and then take a look. The next one here is just a side view of the same. And there was actually something interesting here. So if we look at the bottom right on the heel, So you see how that liner has some space with the outside shell. Anytime you put on a ski boot, you should tap your heel about 3-4 times to get that heel all the way back. If you see that little cupped area, and it's kind of hard to get the boot on. So you want to tap that heel 3-4 times on the ground before you buckle up, and it'll push everything back and it'll fit better. And these may seem like small movements, but it's the difference between being unbelievably tired or not at the end of the day. So yeah, bottom up slicing and slicing on the side. And then we just took a couple of screenshots. So we obviously had a stick in there just to kind of hold it up to do the scan. And then a buckle. This is kind of interesting. So all those buckles, not all of them, but very often actually have a screw. So, if you latch something and this one's too tight, the next one's too loose, you can actually make a kind of a fine adjustment there. And then we were hoping to find something. We did a high mag on just the toe, but it really wasn't anything too fascinating. So the technique info on the toe or the AOI scan, 220 kV, used a Varex 4343 and the Microfocus RT. The helical scan, we just, for geography reasons, put it on a little bit bigger system. So 440. The 450 RT, we certainly didn't need that for penetration. It was honestly probably just a bigger box, and then a 4343 panel. So the next Scan Your Passions one, this is Mac. So Mac is really into music, and specifically he's always been an enthusiast of records. So I didn't know this till we started our Scan Your Passions activity. But apparently digital audio files get compressed and make the files small enough to store. That part I knew, but the vinyl doesn't do that. And so there's little nuanced audio pieces that can be lost. And so it's kind of turned into this cottage industry and cottage activity, and Mac's pretty deep into it. So, the other big deal, I think, and again, probably dating myself, but, for some of our younger employees or younger teammates, the idea of getting a whole bunch of songs all, in one place is, that now it's cool again, I guess. But so he buys these, and this is what he wanted to scan, was basically the read head from that turntable. The other thing is they have, pretty cool artwork here. So I asked Mac to throw a few of these together. So turntable cartridge. So it ended up being 3 separate scans, one as is, and then one for the stylus, and then, kind of aligned everything all together. Sometimes when you're scanning more for show and less from a technical perspective, if you've got plastic and metal together, we're always going to get some level of streaking. You can get some of that out with software. We can get some of it out with filtering, with techniques, that sort of thing. But in this case, it made sense to just pull them apart. So here's Mac's work, and obviously did this in VG for anyone that's not as familiar with X-ray and CT. And his technique info. So the cartridge, stylus, and cover were all at about 220 kV, and using the Nikon Microfocus RT, and a 1621 was used across the board. He did try and scan an actual record, but it really didn't turn out to be much. Any of the bumps in that, you'd have to break a very, very, very tiny piece off. And at this point in the presentation, everyone knows about geometric mag. And so if I've got a record spinning around 360 like this, I'm not going to get really high mag. It would have to be really, really close to the face of the X-ray tube. So next one's a model train. So Jeremiah in our lab is a collector of model trains, and So the materials in that locomotive are primarily plastic or low density cast materials. And he did have to do a little bit of disassembly. The shell is made of styrene and Delrin. Zinc tin alloy is for the chassis, which I actually found kind of interesting. I had toy trains when I was a kid, but they were all metal, whereas they actually use that extra weight so they keep contact with the rails. And the dense components are steel pins and screws. So other materials are brass, copper, and printed circuit boards. So this one actually did find something kind of interesting. So we scan complex assemblies every day of the week, right? Whether it's a medical device that's assembled, actuators or different components that go into the aerospace world, the automotive world. All of these materials are very common to see in a CT lab. And sometimes people have problems with their parts. In this case, Jeremiah actually bought one of these trains online. There's a particular one he was looking for. And the drive gears would bind or stop. And what he found is that he was actually missing one. And of course, who sold it to him didn't anticipate it was going to get CT scanned. But that worm gear was missing. So it ran at about half the power, half the speed, which was very, very interesting. And so with that, Jeremiah also threw together a pretty cool video here. So with the multiple scans, I believe he basically overlaid these within volume graphics. So the low density and the high density, as well as the total scan, so that you can surface things differently, for more for show than anything else. But that's not uncommon for customers to need this level of information, especially if they're reverse engineering something. All right, so technique info. So use 220 across the board, and then reflection on the whole train. He used the RT on the plastic scan and the reflection on the metal. So honestly, I'm gonna take a stab at it and say that was probably availability that day more than a technical selection, which anybody that has a few X-ray machines, that's also a real world situation. All right, the Xbox. So I think Justin presented this at AS&T Digital, maybe. This is kind of a cool story. So different people, different passions. So Justin is dominant at fantasy football and at gaming. And so in the early 2000s, the Microsoft Xbox had an issue called the red ring of death. They, after they shipped these parts out, basically didn't anticipate that some of these gamers were going to sit there and play on their machine for 12, 14 hours at a time, and it would end up heating up. And so there was cracks in BGAs or cracks in the circuit card that would open up when they're warm, close up, open up, close up. And so it was known as the red ring of death because there was basically 4 red quarter circles that would light up, and when all 4 of them were lit up, your system was dead. Cost Microsoft a little over $1 billion to fix this problem that very likely could have been caught earlier on with some CT scanning. So Justin bought one off of eBay. Unfortunately for the testing we did, it was not a failed one. But this is very analogous to something we do every single day. We look at printed circuit boards, and you've got that high and low density navigation. You've got the size of that card versus the resolution that we want. If we've got a big card, that can be a challenge. Identifying and locating those issues or those breaks. The issue causing the red ring of death was that PCB would get hot when it was used. It would cool down, be hard to find, and the solder balls on the board were not designed for that repeated cycling that resulted in cracking. So here's a video that Justin came up with, and this is, of course, mocked up in VG. And they did do multiple scans. I think they did an extract or a laminography on the board, as well as an overall. So if you're looking for head and pillow or something like that, that's really where that laminography, which I didn't touch on. I know the presentation was going to get a little long the way it is, but laminography is basically an X-ray tube here, detector here, and we move them in this type of a fashion rather than a full rotation, so you can get very, very high magnification on a 8, 10, 12, 15-inch circuit card, but you can still get very close to the X-ray tube. So technique information. So the whole box scan at 220 using the RT, using a PE or Perkin-Elmer, which is now Varex. The shell scan. So again, at 220 using the RT in the 1621. And the motherboard BGA scan. So we used a extract 60 degree scan angle and about 160 kV and a 2520 DX panel. And that's all I've got. So any questions, thoughts, by all means, add it to Karen or George in the chat, and I'll be happy to field them best I can. I think
Thanks,
you're
I'll
still...
get on. I was Karen, you're muted.
Yes,
Took me a
I
minute to get
am.
on.
Just checking to make sure you're paying attention.
Well, it took me a minute to get on.
All right, everyone's got to wake up now.
I've been eating potato chips and watching the presentation. That was very good, Ben. I really enjoyed that. Anyway, so I had potato chip in my mouth. Had to finish chewing it before I got online. You ended too fast.
Yeah.
Very well done.
I should have put a stack light on the side so everyone knows when to wake up, right?
Yeah. Well, Karen, do the attendees, can they chat? Because it looks like, I'm not sure they have access to the chat yet. There is the question and answer box, and I don't know if we can maybe, yeah, there you go. You can probably give permissions or something.
Well, I'm allowing everyone to talk. However, they've got to do the same thing I did and unmute themselves if they want to ask a question. The chat box is open.
Yeah, I was looking at the chat box for me to send a chat. I can only send a chat right now to host and panelists.
Hmm.
I don't know, that doesn't necessarily mean they can't send it to us also, but. Oh, technology is good stuff once we get it worked out, details worked out. Well, so your expert skier video you had there, Ben, that was your youngest, right?
Yes, that is Teddy. Yep. He's
Yeah.
so he'll be starting in the ski club this year. Yeah.
Awesome.
Yeah.
Yeah, snow skiing is not anything I've done. So
Hmm.
one of these days I'll have to join you up there and see if I can keep from breaking a leg or something.
Yeah, bring it on. Yeah, it's no, I certainly enjoy teaching it. Yeah, it's been a lot of fun.
So I used to work when decades ago. I worked for the railroad indirectly. I was under a contract with the railroad, Burlington Northern in
Yep.
Memphis, Tennessee, when I went to University of Memphis. And so I unloaded automobiles. But anyway, the reason I brought that up, I thought the rendering of the volume graphics on the train engine was awesome, and it was also from what I understand, was that color correct? I mean, didn't the
Yes.
actual green was the Burlington Northern
Yeah.
green? So
Yes. So that was actually my dad retired as a conductor from the BN. So yeah, that was absolutely correct. So actually showed that to my dad because Jeremiah is a significant train enthusiast. So yes,
that was beautifully done, and that takes an additional skill to be able to pull all that kind of stuff in. We don't normally do that, I guess, in our regular everyday inspections, but that's anyway, I was impressed with that for sure.
Yeah.
It was very impressive. I really like the way that we could slice it in both directions and see things. But you mentioned flight hardware and aircraft or rocket parts. So how do you qualify your systems and your team to reach the approvals from the clients?
Sure. So most of the aerospace customers have some kind of a on the team side, most of them expect NAS 410. So everyone in our office that's going to do or deliver a CT scan is going to be a level 2 or a level 3 in NAS 410. And within our written practice, we define, digital X-ray, we define CT, we define these different things and how they're going to be qualified. I mean, the traditional testing process holds true whether it would be, MAG or UT or X-ray, CT, whatever, but they take a general, practical, and specific so that we're confident that they can find the defects, that they can make a scan, that they aren't just a button pusher, but they're a confident tech that can make a good scan.
Right. Competent tech is the important rule.
Yep.
So I see where a project like this would really hone someone's skill set to, I mean, we get used to doing the same type of part or the same type of configuration over and over and over again. But having the different mixes of materials would be fascinating, I think. So I have something from Joatam, and it says, I missed the last part of PCBA, how the CT scan helped to find the problem of the death of the ring. How did the CT scan help to find the problem of the death ring?
Yes. So the actual Xbox that we had did not have this defect. But I can actually I'll bounce back a couple of so the issue was the PCB was getting too hot when the console was being used. So the solder balls, so these are solder balls. If you had a defective one, you would easily be able to see that void or that defect that's breaking apart. I'm not a expert in printed circuit boards, but very, very common defects within printed circuit boards is what they call a head and pillow. Basically, it literally looks like two of these balls smushed together. And that's the most common way that those things are going to crack. And so I'm speculating a little bit, but if that would have had head and pillow, we would have seen it. I mean, I think this is fairly good evidence, but that, the eBay Xbox that we bought, 18 years later, 20 years later, did not have the defect we hope to find.
Well, it's a real bummer you didn't get a defective one.
I know that's part of this, these adventures, right?
Only in our world would that be a bummer
Yeah.
to not buy a faulty part.
He got what he
is-
paid for. What's up with that, right?
Yeah. Well,
Yeah.
I will say it's emblematic of an X-ray house or a CT house, and anybody that does CT scanning and probably second this is, you'll have someone come in and say, I have a problem, and we can X-ray it, make a really good X-ray or CT scan. And, I see the list of attendees here. Lots of other people can too. Sure. And, in aerospace, that's why we want RQIs, right? In critical applications, that's why we want a known defect, and then I can prove to you, I can see it, right? So, yeah, this
We
one
want that
did
in the
not.
maritime industry as well.
Yeah, there's
So I have a question from Alan Sanders. It's what type of part, material, or configuration are the most challenging?
oof. Everything's got a challenge, right? Boy, I don't know. So the easy one would be density, right? So if you and by the question, I'm gonna guess that we take the periodic table of elements, and as I go down and as I go to the right, things get more dense. So there are certainly rocket parts today. There are certainly defense items today that are getting bigger and thicker and printed in such a way that eventually you can't get x-rays through it. We up to in our shop we go to 450 kV. We have some friends or partners that have MEV, but even the MEV has challenges, right? So I would say thickness and density is probably a challenge. Whether I could spend a month telling you about what's tough and challenging. Hopefully that answers it.
Well, I think that answer, if I asked 20 technicians, I would get 20 different answers for that
Yeah.
one. I mean, it's pretty much a loaded question.
Yep. That's a good question for sure.
Yes. I love this image that you have up. It almost looks like something out of Star Wars.
Yeah, it's BGAs surface really well. They surface very, very well.
Yes. Okay, so what are some interesting developments that you're seeing for Avonix in 2023?
Well, so we've certainly been hiring and growing a lot. Some of the scans that were done here were done on known tube and known X-ray detector combinations, but we've got a couple of new machines that we built that we're just kind of waiting for a public release. That's why I had a fuzzy image there. I mean, they're real. I could walk you back to them, but we're going through kind of a product cycle with Nikon right now. So we'll have some new models in the new year for sure. And we're growing quickly. So we're in the process of signing a lease for a new manufacturing site. Got designs done and that sort of thing. So
Excellent.
yeah, new teammates, new place, and new tools.
Well, I look forward to getting another talk with you in the future
Yeah.
about the new things that you're doing.
Absolutely.
Ellen says, thanks for the answer and thanks for the presentation.
Yeah, for sure.
So, okay.
All right.
Well, thank you so much, Ben. I really appreciate it. Everybody, this is
Awesome
again
job.
Ben Connors from Avonix. I really appreciate him being willing to donate his time and expertise to help the community.
Yeah, absolutely. Well, thanks again for setting it up, and yeah, I'm sure we'll talk soon.
Next week.
Yes, we'll see you in a week. All right.
Absolutely.
Sounds good.
Thanks. Bye.
Thank you.
Bye.
Thank you.
Bye.